Good morning, everyone. Thank you, the chairman, for the introduction. Today, I will present some experimental results on the corrosion behavior of L PBF maraging steel in contact with molten aluminum. So nowadays, there is a growing interest in the production of increasingly large, complex, and thin-wall structural casting product produced via high-pressure die casting. Aluminium, silicon, and magnesium is one of the most industrialized alloys for this kind of application. However, at the European level, there is a growing push to reduce the use of critical raw material by promoting aluminum alloy with a lower percentage of silicon. One such alloy is the aluminum silicon 7 magnesium, typically used in gravity casting. However, decreasing the percentage of silicon in the alloy results in a higher melting temperature that causes an increase in corrosion of the steel mold. So there is a need to optimize mold to increase the service life, enhancing productivity, for example, through the implementation of high-performance insert with conformal cooling channel. Maraging steel is a class of steel characterized by high tensile strength together with good utility and thoughtfulness. The low-carbon martensite matrix, together with the presence of nano-size intermetallic precipitates, are responsible for the peculiar mechanical properties. Furthermore, the low carbon content enhance the dimensional stability of the alloy that, together with the low coefficient of thermal expansion, make them easily weldable and so easily processable via L PBF technique. Indeed, this technique was recently adopted in the molding and tooling industry to produce insert with conformal cooling channel capable of improving the productivity. These components usually undergo severe stress condition and suffer from corrosion due to the contact with the molten aluminum when no protective layer are employed or where this layer are damaged by wear. So the aim of this work is to evaluate and compare the corrosion resistance of maraging steel samples in contact with molten aluminum produced by both L PBF technique and by conventional route. The sample under investigation were industrially produced. As regard the L PBF sample, they were produced starting from a commercial powder, namely printer powder fort, that is similar for the 1.2709 alloy for the obtainable mechanical property, but with a slightly different chemical composition. For what regard the first sample, they were cut out from a forged round bar, and for both the material, the samples were tested after each treatment with the treatment parameter chosen in order to obtain a similar hardness value. Furthermore, also H11 die casting steel sample were also machined and compared. The static immersion test apparatus involved the use of an electric furnace equipped with an graphite crucible. The aluminum alloy was a primary aluminum silicon 7 magnesium alloy with a low iron content. Approximately 1 kilogram of alloy was melted for each test and held at 740 degrees. A pair of samples of the same material were cleaning with acetone and then submerged in the liquid bath supported by tungsten wires. 4 different immersion time were chosen for the test, and once the samples were moved from the bath, the wires are cooled and the aluminum alloy was poured into permanent mold. So then the cross-section of the immersed samples were cut and mounted in a hot resin to conduct a metallographic analysis. Before the immersion test, also microstructural characterization was conducted. Here you can see the typical microstructure or a vertical cross-section of the AM samples with a semi-elliptical melt pool boundary clearly visible also after the aging treatment. No porosity was detected within the microstructure, suggesting the achievement of a fully dense part. At higher magnification, the scanning electron microscope image instead revealed extremely fine continuous cellular structure, typical of AM part. On the other hand, the microstructure of forged samples reveal packets or blocks of flat type martensite with a very fine and edge boundary, following a needle etching, while after fry reagent etching, the different orientation of the martensite block can be instantly recognized. And finally, for completeness, also the microstructure of the H11 sample was also presented here. Here you can see an example of the sample surface before and after the 1 hour of immersion test. The parameter chosen to evaluate the corrosion resistance was the thickness loss. So before the immersion, each sample was measured by a caliper, and at the end of the test, the final thickness was measured in the cross-section of each sample using a digital microscope. Here you can see on the left side the plot of the thickness loss versus the immersion time. As can be noted, the maraging AM sample present a better corrosion resistance with respect to the forged one. In fact, it was not possible to evaluate the thickness loss after 4 hours of immersion due to the highly dissolution of the forged sample into the molten aluminum. On the left side, the average thickness loss was plotted again the square root of the immersion time in order to underline the linear relationship indicated that, as expected, the consumption of the steel sample is controlled by the diffusional process. Furthermore, as can be noted, the sample cross-section of additive manufacturing maraging steel sample results more uniform, results in a more uniform dissolution as compared to the forged one. This behavior could be correlated with the different speed of the reaction between the steel and the aluminum, or probably could be also related to some effect related to the more uniform microstructure of IM sample compared to the forged one that present the typical segregation band of forged products. However, further analysis are needed to better understand this behavior. The morphology of the different layer formed after the immersion test is presented in this optical microscope image. As can be noted, some common features are present for each sample. Dense intermetallic layer is present near to the steel substrate, followed by a mixture layer composed of intermetallic particle and aluminum alloy. And then it's possible to see on the soldered aluminum side the presence of typical dendrites aluminum surrounded by the authentic silicon particle. And furthermore, also some intermetallic particle precipitated in the melt can be recognized. However, the thickness of the intermetallic layer, together with the shape and size of an intermetallic particle, is different, differs between the considered sample, where in this case the thickness of the layer on the maraging for the sample was thicker, while the less thick layer is that of H11 sample. Here we can see the scanning electron microscope image of the cross-section after 2 hours of immersion. As can be noted, the intermetallic layer on maraging forged sample results less adherent to the substrate, and it's characterized by a thickness that is less or more double with respect to that on AM samples. The presence of different alloy elements, however, make the interpretation of the different corrosion behavior not so easy. However, according to the EDS analysis, the intermetallic layer on the IM sample is mainly composed of 2 different phases, while only one phase is identified for the forged sample. Furthermore, the presence of more silicon in the intermetallic layer of the AM samples could be responsible for the reduction of the interdiffusion of iron and aluminum atom with respect to the forged samples, promoting higher corrosion resistance. Furthermore, also the effect of different quantity of the alloy elements can influence this parameter, and so promoting the superior corrosion resistance of AM sample. Finally, here is presented the cross-section, the scanning electron microscope image of the cross-section of the H11 sample after 2 hours of immersion. Also in this case, the intermetallic layer is mainly composed of 2 different phases. In this case, as can be noted, the chromium carbide particle results well embedded also in the intermetallic layer, which according to the literature promotes a sort of physical barrier to the diffusion of iron and aluminum atoms, and determine the highest corrosion resistance of H11 samples. In conclusion, it's possible to say that immersion tests highlight the superior corrosion resistance of additive manufacturing sample compared to the forged one. H11 sample possess the highest corrosion resistance and the lowest corrosion rate due to the presence of chromium carbide particle in the intermetallic layer. Maraging additive manufacturing sample exhibit a more uniform dissolution compared to the forged one that can be related to the different speed of dissolution, but also probably to some effect related to the more uniform microstructure of AM samples. However, due to the slightly different chemical composition between the maraging tested sample, it was not possible to understand if there is or not a possible influence of the microstructure on the corrosion behavior of the sample. So short-time immersion tests are needed to evaluate the possible influence of the microstructure on the corrosion resistance of maraging steel AM sample. And thank you for your attention.
Thank you very much. Very interesting talk. Is there any question from the audience? If not, I have a question. Did you also change the composition of your corrosive media?
I'm sorry?
Did you change the composition? Did you change how corrosive your media is? Did you make another media?
Yeah, we have to try now. So, because it's a part of a work that's involved the use of recycled aluminum alloys. So we have to analyze now what's happened when the more iron is present in the aluminum alloy in order to better understand how molten insert can compete also with a recycled alloy. So we have to better understand maybe if or not there are possible effects on the microstructure on this kind of material in order to tailor the microstructure to gain a superior corrosion resistance.
Mm-hmm. Okay, thank you.
Thank you.